Dear students, in previous class we learned about trigonometry, and in the trigonometry we learned multiple and trigonometric ratios and compound angles and multiple and submultiple angles transformations. So like this we are learned some chapters from trigonometry. Now another chapter today we learn, that is complex numbers. So let us see complex numbers introduction. In this class the objectives are, on the completion of this period you would be able to define complex numbers, problem algebraic operations with complex numbers, state properties of complex numbers. Introduction. We recall the solution of quadratic equation. Ax square plus bx plus c equals to 0, where a is not equals to 0. Consider it as a equation 1. With real coefficients a, b, c is given by real numbers x1 and x2, where x1 equals to minus b plus under root of b square minus 4ac by 2a, and x2 equals to minus b minus under root of b square minus 4ac by 2a. If b square minus 4ac equals to 0 or greater than 0, for b square minus 4ac is less than 0, we do not have a solution of 1 in the set of real numbers, because there is no real number whose square is negative. Let us consider a quadratic equation x square plus 1 equals to 0, which has no solution in the set of real numbers, because there is no real number whose square is minus 1. In order that such equations to have solution, let us extend our set of real numbers to a new set of numbers called complex numbers. In the 17th century, Euler has introduced the symbol I with the property I square equals to minus 1, and the solutions to x square plus 1 equals to 0 were written as x equals to plus or minus I. Definition of complex number. An expression of the form x plus iy, where x and y are real numbers and I equals to under root of minus 1, is called a complex number z. A complex number can also be defined as an ordered pair of x comma y of real numbers. Here x is called the real part and y is called the imaginary part of the complex number. We can represent x equals to real part of z or re of z and y equals to imaginary part of z or im of z. For example, minus 4 plus 7i comma minus 1 by 4 plus I into 0 comma 0 plus I etc. are complex numbers. Equivalently, they can also be represented as minus 4 comma 7 comma minus 1 comma 0 and 0 comma 1 etc. Algebraic operations with complex number. Equality of two complex numbers. Let z1 equals to x1 plus iy1 and z2 equals to x2 plus iy2 be two complex numbers. Then real part of z1 equals to real part of z2, that is x1 equals to x2, and imaginary part of z1 equals to imaginary part of z2, that is y1 equals to y2. Two complex numbers are equal if and only if their real and imaginary parts are separately equal. Next, number 2, second point. Addition, subtraction, multiplication and division of two complex numbers. Let z1 equals to x1 plus iy1 and z2 equals to x2 plus iy2 be two complex numbers. Then z1 plus z2 equals to x1 plus x2 plus I of y1 plus y2. z1 minus z2 equals to x1 minus x2 plus I of y1 minus y2. z1 into z2 equals to x1 x2 minus y1 y2 plus I of x1 y2 plus x2 y1. Fourth point, z1 by z2 equals to x1 x2 plus y1 y2 by x2 square plus y2 square plus I of x2 y1 minus x1 y2 by x2 square plus y2 square. Properties of complex numbers. First, addition is cumulative. So let z1 equals to x1 comma y1 and z2 equals to x2 comma y2 be two complex numbers. Then z1 plus z2 equals to z2 plus z1. So commutative property. Second, addition is associative. If z1 equals to x1 comma y1 and z2 equals to x2 comma y2 and z3 equals to x3 comma y3. Then z1 plus z2 plus z3 equals to z1 plus z2 plus z3. Next, properties of complex numbers. Addition is commutative. Let z1 equals to x1 comma y1 and z2 equals to x2 comma y2 be two complex numbers. Then z1 plus z2 equals to z2 plus z1. Addition is associative. If z1 equals to x1 comma y1 and z2 equals to x2 comma y2 and z3 equals to x3 comma y3, then z1 plus z2 plus z3 equals to z1 plus z2 plus z3. See the here brackets are mentioned in the left side last two terms and the right side first two terms. So this is associative. Addition is commutative and addition is associative. Existence of zero. The complex number 0, 0 is the identity for addition. It is called zero complex number. If z equals to a comma b and 0 equals to 0 comma 0, then z plus 0 equals to 0 plus z equals to 0. Additive inverse. See here in the third point, z plus 0 equals to 0 plus z equals to z, not 0. The here wrongly printed. So observe here, that is printing mistake. Next, fourth point, additive inverse. If z equals to x comma y, then minus z equals to minus x comma minus y is called additive inverse of z. That is z plus of minus z equals to x minus x comma y plus of minus x comma minus y, that equals to x minus x comma y minus y, that equals to 0 comma 0. That is minus x minus iy is the additive inverse of x plus iy. Multiplication is commutative. If z1 equals to x1 comma y1 and z2 equals to x2 comma y2, then z1 into z2 equals to z2 into z1. Multiplication is associative. If z1 comma z2 comma z3 are complex numbers, then z1 of z2 z3 equals to z1 z2 of z3. So, multiplication is commutative and associative. Seventh point, existence of multiplicative identity. The complex number 1 comma 0 is the identity element for multiplication. If z equals to a comma b, then z into 1 comma 0 equals to a comma b into 1 comma 0. That equals to a comma b, that equals to z. Multiplicative inverse of x plus iy is x minus iy by x square plus y square. Now we see the problems. First problem. Express 1 plus I by 1 minus I in the form of a plus ib. Solution. 1 plus I by 1 minus I equals to 1 plus I by 1 minus I into 1 plus I by 1 plus I. Here, for LHS, we are multiplying and divided with 1 plus I. That equals to 1 plus I whole square by a plus b into a minus b means a square minus b square. That is 1 minus I square. 1 plus I square means minus 1. Sorry, in the numerator 1 plus I into 1 plus I, 1 plus I whole square means a square plus b square means minus 1, that is I square means minus 1 plus 2ab. 2ab means 2 into I by 1 minus of I square means minus 1. So 1 plus 1 minus of minus plus. That equals to 1 minus 1 get cancelled. So 2i is there in the numerator, and in the denominator 1 plus 1 means 2. So 2 get cancelled. So only I is there after cancellation. That equals to 0 plus I. This is in the form of a plus ib, where a equal to 0 and b equals to 1. Next problem we will see. Find the real and imaginary parts of 4 plus 2i by 1 minus 2i. Solution is let us take given statement or question, that is 4 plus 2i by 1 minus 2i. Then to this multiply with 1 plus 2i and divided with 1 plus 2i. Then in the numerator, if we multiplied or if we with the another numerator, so we will get 4 plus 8i plus 2i plus 4i square, because 4 into 1 4, 4 into 2 8i, and like 4 2i also multiply with these two terms. So 2i into 1 2i, 2i into 2i 2i whole square, that is 4i square by the denominator, the products are in the form of a minus b into a plus b. Then we can write a square minus b square. So 1 square means 1 minus b square 2i whole square, that is 4i square. I square means minus 1. So minus into minus plus 1 plus 4. that equals to 4i square means minus 1, so minus 4 plus 4 minus 4 get cancelled. 8i plus 2i means 10i by 5, that equals to 2i, and here real part equals to 0 and imaginary part equals to 2. Next question, third problem. Next question. So here real part equal to 0 and imaginary part equals to 2. In the second problem, we already know. Now third question. Find the additive inverse of a minus ib by a plus ib. The solution is, let us write what is given. Given is a minus ib by a plus ib. To find the additive inverse, first we have to kept it in the form of a plus ib. Then we can easily write additive inverse of a plus ib, that is minus a minus ib. So to convert a plus ib for given question, we are multiplying and dividing with a minus ib. So then it becomes, in the numerator, a minus ib into a minus ib means a minus ib whole square, by in the denominator the two products are in the form of a plus b into a minus b, then it becomes a square minus b square. So minus ib whole square means I square b square. I square means minus 1. So minus into minus plus. So a square plus b square. Next, that equals to, if we expand the numerator in the form a minus b whole square means a square plus b square minus 2ab. So here a square plus b square means ib whole square. I square means minus 1. So that's why here minus b square is written. Minus 2ab, b means ib, by a square plus b square. Next, if we split the denominator to the above numerator, see how we are separated here. In the numerator we have a square minus b square term, so a square minus b square by a square plus b square minus, and 2ab into I by a square plus b square. So now this is in the form of a minus ib or a plus ib. So now we can easily write its additive inverse. I already told you, again here giving, if the complex number x plus iy, then its additive inverse is minus x minus iy. So additive inverse is, now for this given question, is minus of a square minus b square means, if you multiply with minus, we have b square minus a square by a square plus b square, and minus of minus plus, so 2ab into I by a square plus b square. So this is the solution. Next question and next problem. Find the multiplicative inverse of the complex number 6 plus 20i. Solution. Find the multiplication inverse of the complex number 6 plus 20i. The solution is, we know that if the complex number x plus iy, then its multiplicative inverse is x minus iy by x square plus y square. Then the multiplicative inverse of 6 plus 20i is 6 minus 20i by 6 square plus 20 square. That equals to 6 minus 20i by 6 square means 36 and 20 square means 400. So 436. This is the multiplicative inverse of the 6 plus 20i. Next, summary. We have discussed about definition of complex numbers, algebraic operations with complex numbers, properties of complex numbers, problems solved on various properties. Quiz. The additive inverse of x plus iy is, so these are very easy. This is very easy question. So see, the additive inverse of x plus iy is, answer is A. So just put the negative symbol for real part and imaginary part. That means opposite sign. Okay. Next, the multiplicative inverse of x plus iy is, this is also the direct question, we can say it is a formula. Okay. So the answer is B, that is x minus iy by x square plus y square. Third one, if z1 equals to x1 comma y1 and z2 equals to x2 comma y2, then multiplication is commutative. So answer is C, that is z1 into z2 equals to z2 into z1. Next, frequently asked question in examination. Find the real and imaginary parts of the following: 4 plus 2i by 1 minus 2i. And so once again we recall the what we had learned in this class or PPT, from the PPT. See, complex numbers. This is a set of numbers. We already know the some number sets: natural numbers and whole numbers, integers, rational numbers, irrational numbers, real numbers. So in this order, real numbers are a big set, but in the real numbers there is no complex number. That means if we square the any number, we did not get -1. So that means another number set is there which is bigger than real numbers. So the another number set is nothing but complex numbers. So in the complex numbers we have all these number sets, that is natural numbers, whole numbers, integers, rational numbers, irrational numbers, real numbers. So we are learning a big set. That means big number set, that is complex numbers. So we are defined complex numbers and its operations with complex numbers perform and properties of complex numbers. See here, one point is there. In quadratic equation, x square plus 1 equals to 0, which has no solution in the set of real numbers, because there is no real number with square is -1. But in the set of complex numbers, it has a solution. So that's why we are extended our set of real numbers to a new set of numbers called complex numbers. In the 17th century, Euler has introduced the symbol I with the property I square equals to -1, and the solution to x square plus 1 equals to 0 were written as x equals to plus or minus I. So I equals to, we can write under root of -1, and complex numbers form is x plus iy, where x is a real number and y is a imaginary number or imaginary part. Next, algebraic operations with complex numbers, that is here we know how to add and what is real part and what is imaginary part. Next, how to subtract, how to multiply, and how to divide also. Next, properties of complex numbers. So addition is commutative and addition is associative existence of 0. If z is a comma b and 0 is 0 comma 0, then z plus 0 equals to 0 plus z equals to z. Here 0 is printed wrongly, so correct it as a z. Additive inverse. Z plus of minus z equals to minus z plus z equals to 0, then minus z is the additive inverse of z. Multiplication is commutative. Z1 into Z2 equals to Z2 into Z1. And multiplication is associative. That means Z1 of Z1 Z1 of Z2 Z3 equals to Z1 Z2 of Z3. See, the brackets are changed its positions. So existence of multiplicative identity. Z into 1 comma 0 equals to Z. The complex number 1 comma 0 is the identity element for multiplication. Next, multiplicative inverse of x plus iy is x minus iy by x square plus y square. So these are the properties or formulas, and after this we learned problems how to express in the form of a plus ib the given question or statement which is in the complex number and mixed with real numbers and having numerator and denominator. Next, from the given question we are found the real part and imaginary part by simplification. How we simplified, how we solved means we took the conjugate of the denominator and we are multiplied and divide to the given fraction. And to find the additive inverse, if the question is in the fraction, then from that fraction first we have to change that fraction into general number, like without denominator. We have to frame that, or we have to express that question. How? Same again here also we are took the conjugate of the denominator and for the fraction we are multiplied and denominator, and finally we got it is in the form of a plus ib. Then we can easily found its additive inverse or multiplicative inverse, whatever the question is. And here two are important formulas generally. Additive inverse of x plus iy is minus x minus iy, and multiplicative inverse of x plus iy is x minus iy by x square plus y square. So very important. Additive inverse is and multiplicative inverse is both are change. So very careful while you are writing. Is it observe, is it additive inverse or multiplicative inverse of the complex number? And if you know the rationalization or its conjugate number, then you can easily solve the questions, because here the simplification is very simple. Just you have to know how to multiply, how to divide, how to product, how to add, how to subtract. So very simple basic things are lies in the solution. So and you can do exercise problems based on today's topic or what we learned here in this class, or from PPT. You do the exercise problems, and if you have any doubts, ask me or mail me. And one more thing, while watching the video, you have to open the PPT in another device, because every video is based on PPT, and if the video is not clear or sometimes screen clarity may not visible, then if you see the PPT and if you listen the video or watch the video simultaneously same time, then you can overcome the screen visibility issue or screen clarity. And I think PPT is very clear. And regarding screen clarity, some technical aspects we cannot say whether it is more clear or little clear. So my request is open the PPT and open the video in another device, and you can listen and watch PPT, then it is better. And do more problems so that the formulas will comes in your mind. And each formula write 10 times. If you are facing formula is not easy, then write that formula as a 10 times so that it is fixed in your mind. Thank you.